Hello. Hello, hello.
Hello.
Yep.
Yeah, I'm here.
Okay, let's allow the people to come in.
Mhm.
The host user, one moment. Guanqi, I will make you a co-host so you can add people.
Okay.
Um, okay, so I think someone in the morning asked me to share the paper on the timber recognition, so I will just post this one here. So I have uploaded onto my blog, so you should be able to find it in, like, if you're clicking here, and you should be able to click here and either download it or view it. So this is a paper on the defect recognition and the jointing of the defect timbers optimized for the industrial process. And also I have just sent the email regarding the PowerPoint on the day one, because I'm aware that the video recording on day one is lost due to override in the unfortunate circumstances. So I'm sharing my PowerPoint on the day one. Yeah, if that helps. I'm wondering, has anyone had some time to play with the CNN? Like, we have the code we have distributed in the morning. Wondering. Good. So anyone feel like sharing their own code or the outcome of their iterations?
I won't mind share my result because I thought mine was interesting
Yep.
in I think in a bad way, but I think it's worth it to share.
Sure. Definitely.
So yeah, so this is the first. I ran two CNN training.
Yep.
This is the first one. I didn't really change much from my RNN model in this particular case. I think the one I changed might be the filter. I didn't change the kernel size. So it gave me mm, not a better performance than my RNN result. But I thought when I see the gradient descent, I thought, well, it might worth a try to increase the epochs to allow it to continue to train. So that's what I did. So I increased from epochs from 20 to 40, and this is what happened. Um, so you can see the test and the train.
Oh, That's weird. So did you train the model from start, like, or it's trained on like a pre-trained model? So is it trained based on the previous model, or is it like you just trained like a totally new model? Because I'm just curious, because if it's like if you're just expanding the epoch, like the first 20 iterations should like look similar to the previous ones. So I'm just wondering.
Right. Yeah. I think I'm not quite sure where the mistake lies. So I know for sure when I did the first CNN model, I ran from the top to down. I run every single cell in the code. And in this particular case, I think I may have only run the model structure code cell, and then after that. So that may cause this, but I don't think so because I used the same process I did yesterday. Um, Yesterday I was able to get, I think, pretty accurate result versus this one. I ran out of time to run it again, so I didn't get a chance to see what happened exactly.
So I think this is the reason. So if you look at the upper left part, so this one, like you're having your test and the validation started at approximately 0.013. And if you go back to the previous page, you see it's sort of finished. You can see the value loss. It sort of finishes at the 0.139. So basically, you just pick up from where this one ends and went down training with this model. So normally when we start a new model, we start with randomized like parameters. But after the first iterations, you already have trained the parameters. And I think it's because you have only run the section where it says model fit, but you didn't run the section where it says model initialize, like, or to create a new model. So this one is, instead of training a new model, it just keeps on training like what is already stored in the memory, like the existing model. So actually you're training instead to like from 0 to epoch like 40, actually you're training from epoch 20 to epoch 60.
Cool. Interesting.
Yeah. But potentially you see like even with this very limited structure, like just by increasing the epoch, they are like significant increase in the model score. Maybe I think it's partially because of the structure you're having. It's not as efficient as the one we're seeing in the morning, but you can see obviously this one, it just takes like a lot longer, a lot more iterations to train comparing to the neural net, which probably like we can get a pretty much accurate results in 20 epoch. Like this one, it's already going down to the 60th epoch, and there are still rooms for improvement.
Right, absolutely.
Yeah.
Pretty interesting.
Yeah. So anyone want to share their models? It doesn't matter if you're like having a very good score or like very bad scores. It's just worthwhile just looking at the process and see where are the like benefits, potentials, and where are the problems. Sorry, I'm seeing Yu Qian connecting to audio. Are you trying to say something? Or you're just having a computer crash? So anyone else has some luck with the CNN model? Dead silence. Yeah.
I will
Yeah.
share mine.
Yeah.
Oh, okay, where is this?
Yeah.
Oh, okay, this is the first part of neural network, and this is the RNN, and this is the CNN.
Sorry, I don't think your like image is changing.
Oh, Or perhaps stop sharing the another. Yeah, can you see this?
Yep.
Okay. This is the CNN result, and I compared with the RNN as well as the neural network. So my lowest score in this part, I only ever try for twice. So this is the lowest score that I can get.
So, just so this one you're having 81. Yep. So I think yours are having a very similar structure to Boshan. And so if we're looking at the epoch, can you zoom in to the epoch numbers? So, and I think you guys are having very similar results. So you see like he has been lowering from like 0 to 20 and from 20 to 60. So it's like a very similar trend. And I think also because I think like the model structure is very similar. So just some thinking in the process. Can you go back to your model structure? So this so right now, like we're looking at this one, so we already have one like convolution co 1D. Sorry, it just looks so much like COVID, like one COVID layer, convolution 1D layer, and then we're having like 4 dense layers. Just intuitively take a guess. So considering like the kind of data structure we're having like 20,000 like data sets. Each one, like the input is about 80 dimensions. The output is about approximately 82 dimensions. And we're trying, and we sort of have an intuition understanding like the connection is not that complicated. It's we're trying to catch the relationship between the material thickness and the bending properties. And just some intuition, if we're looking at this structure, if we were to improve it, shall we increase the layers or shall we decrease the layers?
I think we probably reduce the layers.
So let's try something because this one the training process is quite quick. So maybe I'll start to sorry, I'll just leave you screen on and I will start with this model structure here. Just give me a second. I'm turning on my Jupyter notebook. Oh, by the way, and since we're already here, and can you guys try to send your PDF files to Guanqi because he will be responsible for putting together to make video for the group. It'd be quite helpful if you guys can share your work with him.
Yeah, no problem.
Yeah. Models. So currently we're having a model of the first layer is 32, second layer is, one moment. Just trying to read. About flatten, let's just get rid of the dropouts. And the next layer is 512. And the next one. So what kind of optimization are you using? Are you using the SGD or are you using ADAM? One to 8. 64. So learning rate is 0.05 negative. Yep. So I'll start with. Okay. Can you stop sharing your screen? I will start to share mine. Yep. Thank you very much. So this is your, so assume we are starting with, maybe we only limit it to 50 epoch, and we see what we will have. Sorry, I need to run from the start. So in this case, we only have one dense layer after the COVID one. That is like a layer of like 64 neurons, which will give us, right, I'm having some weird results in the previous iterations. Feel free to pull up your code and just play with them a little bit. Because I think a lot of intuition about how each neural networking have to come from like this kind of comparison of different iterations and just a combination of the like different parameters. So obviously this one, so we're halfway through. So I remember at the 20th epoch, originally you're at something like 1.0. One moment. Yeah, so I think it's similar. So it originally you're also at the mean absolute value of the, here. Yeah. So comparing with this one, so this one I'm having a far smaller neural nets, but at the 20th iteration, I'm already at something that is like 0.138. So this one, even though it's a lot smaller, you would notice it actually perform like similarly with, so this one is, we only have one dense layers, like, and get rid of like all those dense layers in the model, which basically reduce like 700 neurons. Like one layer of 500 neurons and another layer of 128 neurons. So we would notice that even though this one was significantly reduced in size, but in fact, like the accuracy, sorry, at the 20th epoch, so we're having this one. So this is our 20th epoch. It's very similar to what you originally have, but like the difference comes later, like in the later parts when so this one's at 50th epoch. This one didn't reduce like as much as yours. So, but you will see it still looks like there seem to be still potential, but in the like a later part, it's just have like a more gradual rate of learning. I think it's partially because we're having a learning rate decay here. So let's see if we run it for another 50 iterations. You can see like the accuracy still sort of consistently improve. No, I think now it started to. So the thing about the learning rate decay is that, let me quickly sketch here, since this one is training. So if you actually start to look at the loss value of the learning rate decay, so we see the like one signature if we have reached a plateau of our learning rate is that it start to zigzagging the path or going someplace something like this and cannot find the lowest point. So at the moment where it start to the accuracy start to decrease to a place where it sort of start to going back and forth a little bit, and it will trigger the learning rate decay, and it will just lower the learning rate and go down a little bit more, and then it will trigger some of this kind of bouncing effect, and it will just so those are the places that where if we're using the SDJ are where like the learning rate decay happens. So if we start to
Sorry, I think I cannot say anything.
Oh, sorry. Are you so here?
Yeah,
Okay.
it's okay.
Yeah. Okay. So that if we're don't let's see. So it's very common that you're having some comebacks in middle of this training process. Then to see if your model has some struggle and suddenly it start to going forward again. So this is like when the learning rate decay happens. We have like we change it to a smaller step instead of the big step. Oops. So I think currently we're reaching a threshold of this model. So is it still going down? I'm just going. Let me stop this one. So this one you see like the loss value, it's sort of here you have like start going down from 1138 and go down to like 1131 and struggle a little bit, and suddenly it start to go down once more. So this is like a signature to show that there are still more potential in your model, and sometimes you can increase the accuracy just by decrease the learning rate or just training more epoch. See, but I think currently because this neural net model is overly simplified, it only has a one layer of like 64. Remember, like originally you guys are having those layers and it works really good. So let's say if we're trying to increase the accuracy of this system, shall we add another layer of 64, or shall we add another layer, or shall we just increase the neuron in these layers to like 128? I think this is like some questions we're currently always asking during the training process. Do you add more neurons in this one layers, or do you add like one more layer? Make it deeper or make it like bigger, like wider, like have a bigger layer?
Deeper?
Deeper. So let's say just add another one. So which epoch we're at. So this is like 0.111. Let's take. Remember I have run this one twice. So even though it shows like 50-50, so this one is actually at probably one like 150th epoch. So it's like from 100 to 150th. And then you can see like as we're near the end, it's certainly start to reach the limitation of the model. And you will start to see more of this like bouncing back and out, like back and forth effect with the quality and accuracy of the model. So this is like a typical when you have training like many epoch and your like model is reaching the limitation of its capacity. So this is probably of like 100 to 150th epoch if you're zooming in. So now let's see this one. Just wait a little bit. So while we're waiting, does anyone has more models that you want to show us? Like more interesting things you're like that sort of coming up? It's okay. So this one we're already at 14 and see what happens in the 20th epoch. So I think each one of them perform very similar at the 20th epoch. And the main difference is that if it could still decrease in this rapid speed as it's like reaching towards like as the iteration increase. So I think this one is far better than the previous one. Yeah, I know watching it train is quite boring, so please speak up if you're having other models you'd like to discuss. Oh, quite. So but I think we can have some. One moment. So, so I thought you have show up like this paper in the chat room. Is this something you'd like to discuss, or you're just sharing with people? Hello? Okay. All right, I need to download this one. So the paper you share is called AI plus architecture towards a new approach. So I think this is like one of the earlier paper that discussed this kind of like style transfer issues, and this is like obviously application of the GAN network, like it's called generative adversary network. So basically there are two networks that compete with each other. The typical thing about this one is that sorry, I think I'm sharing the wrong page, wrong computer. Just share this screen. Okay, so I don't know if everyone has opened this PDF. So this is like one of the most common application of the neural net in terms of generative design. As I have mentioned, most of them is built on the GAN network. I am having a very sore throat today. Generative adversary network. And then I'll just show you guys some of the original project of this. So this is what works very good with elements of style transfer, and yeah, Just putting up some general purpose usage, for example. So all of them, I'm not sure about the content of this image, but the essence of this network is that it has two parts of the neural net that I'm going to quickly sketch here. Let's see the whiteboard.
I don't think we can see your sketch.
Okay, one moment. So let's clear the drawing here. So this one is made of, it's a very popular neural network, especially in terms of image generation and the design ROM. So basically this one is having two neural nets. I think we have mentioned it before. One is the generative neural net. And the one is serving as like adversary. Basically means they works against each other. Hope I spelled it wrong. So it's called like GN neural net. So basically has like two neural nets working together in the system. And for the generative net, is that you give it some information. So normally in the realm of design, it could be like a counter curve of the plan. Or sometimes if you're using 3D style transfer, you can give it like a mapping of a building or something. Sorry, my sketch is awful. Or just anything. And in a lot of time, for example, in the generation of the facial features, this one can also taking like a photo of a human. Or sometimes like a photo of two humans. So it can take in like a number of things. And basically what we'll do is that according to the test you're looking for, it will start to draw things. For example, if you're giving it like an encounter of the plan, it will start with by doing like a plan layout of, let's say, this is your bedroom. This is like a, I don't know, like a bathroom, like another bedroom here. And yep. And like, it's just like this kind of very general plan layout. So ideally like this is window. So basically this neural network is a painter or the creator, just consider like this. And this one, the adversary network, what we'll do is that it will look at this one and make a judgment. The judgment is that if this is a plan, a real plan, how do we define a real house plan? It's a plan that we provided as a training material. Basically, if it's a plan that are really made by a designer, so in a term, if it makes sense. And if it can tell like this plan doesn't make sense, it's very different from the like typical features of a like real plan, like a plan made by human. It will give this one like a lower score, like give it a score. Let's just use score for example. There are like, actually those are like vectors of score on different dimensions. So it will give you this one a score. And with this score, this generative neural net, consider this one as a painter. It will make adjustment according to how well it's doing. So ideally, after certain these iterations, this generative neural net, let's say the creator, will work so well that in the end, it will start to generate a plan that with this adversary network, it will be impossible to tell if this one is done by the generative network or it's done by the human. So it's somewhat like a Turing's test, but except we're putting like two neural nets here against each other. So this is like a very typical use of the GAN network. And there are a lot of imaginations in this. Let me see. I'm just pulling up an example. So basically, this one can create a number of things. So this one is something, for example, it can create a plan based on the contour. It can create a model based on the, let's say, the massing. They can transfer this massing into a Zaha Hadid building, and the adversary model will be responsible for making judgment on if this is a real Zaha Hadid building. Like if it looks, let's say not a real, because it has no idea what Zaha Hadid has built or not, but it can see if this one looks like a real Zaha Hadid building. And this one can also work, for example, if you put in two faces, let it to generate a face that has like both features, the characters from both face, and this one just to make a judgment, like to see if whatever you generate is like a real human face or not. So with this one, there are a lot of things that we can imagine. I'm just quickly pulling up this reference. So personally, I don't really like to use that model because GNL model, because for me, like one weakness is that it's always based on the appearance. It's like, does this one looks like a real human design? Does this one looks like a real Zaha Hadid building? It's impossible to tell what that decision is made on. And if they start making up like very crappy designs, it's very difficult to calibrate the like nuance, like why this one work or that one doesn't work. But this one can often work as a miracle. For example, I think in this project, yep. So this project that you're using, so it's using a similar system but different networks, like a similar system but a more nuanced calibrated version of it. So this one is that if you're giving like input of layout, so here are like where the windows are and where the trim are and where the like a door is and where's the column, and it will start to paint an image, paint the facade based on your layout. So this is something that the similar system can also works on. So basically you have like this pixel pix, like the creative generator process. And normally in the training process, you have a like adversary network that make a decision on if this one looks like a real facade or not. And this is like a very similar process. So this one is like, it's basically you give it like a depth map like this one, and it will start to generate a street view based on this like a gradient map of the like depths of the view. And this one's also use like a similar logic. There you have a generator and you have something that start to make judgment if like, so you can see those are the trained GNN models. You have another adversary network that start to make a judgment on if you are creating something that looks like a real street or not. So that is like this interplay of these two neural nets that can generate this result. Of course, the problem is that the generation process is a bit unexplainable. It's very good in adding in the details. So suddenly you have this kind of view depth image, and suddenly you start to have this a lot of details and start to look like a street view. But the tricky thing is that there's no way to calibrate this. There's no way to control, like if you want more stores, if you want more trees, if you want more pedestrians, like why is it generated like this? It's difficult to tell the rationality behind it. It may be okay if you're just looking for this kind of like street view generation, but it would be more tricky if you're looking for some more rationalized decisions such as plan or sections and etc. So those are the So those are the training samples. So I don't think those are the generated ones. Yeah. And I think those are the generated version. So also another thing about the generated version is that let's say because like each iteration and each surface sort of generates in the like they only generate surface and it's so if we're doing like a not generate surface, they only generate image. So if we're doing a video sequence, so this one is a lot harder than it looks because this is a non-linear system, and if there are any tweaks in the input, they will change dramatically at the output. So that if it's a you're working with a video, it's very difficult to get coherence in between frame to frame. That's why like all those AI generated video, there are a lot of this like flickering happening, and it's very difficult to get a very fluent and consistent video. So I think this is one of the better outcomes, but this kind of flickering is just typical features of AI generated video. Yeah. I don't know if that's something you'd like to discuss for this paper, or do you have any ideas or opinions on this paper? Yeah. Thank you. So because so anyone has any other ideas? Because originally I was thinking of like to look at a few model structures, and since like a lot of us didn't really have new model structures. So
for the students or for the individual who is interested in learning AI, or how do you educate, I guess, the next generations in the perspective, in the architectural education perspective?
So I think this is a tricky question because AI, like, because I personally work with this one a lot, but the AI for me personally, it's very, very mathematical heavy. Like everything, even though I can explain it in a more intuitive manner, but for you to really work with the nuance of it, a lot of this one really require like a very in-depth knowledge of how the algorithm works. But I do believe it's like a Grasshopper. Maybe later on, I think now Grasshopper also have a few like AI training like plugins, so it will become more and more intuitive. It's like none of us know like generative algorithm, but or evolutionary algorithm. By the way, I can all use Galapagos in Grasshopper without really knowing like how that happens. But the tricky thing about AI is that currently we're very limited on what computer science can do. The reason why, like most of the AI project, like the paper that you just shared and like the project that I just shared, are very much based on image processing, such as style transfer and etc. This is important. This is typical because this is a part where the computer scientists are more focused on, and they can always have like fancy output, fancy structures that you can just take in and use. So I think it's one, and a lot of them are making them open source, so it's easier and easier. But I think it's like personally, I think there's a danger in this process because we're start to fascinated with the, let's say, the look and style of the things, even though I know like in architecture a lot we don't want to talk about like styles or maybe composition, yes, but like not in the style in the visual manner. We don't want to talk about this anymore. But nowadays I think there's a comeback. So if you're looking at like the recent paper by Matthias or Neil Leach, they start to talk a lot about the styles and the AIs, because the style transfer is just such powerful concept in computer science, and especially in architecture intelligence. And if you're working with them, there are just this abundance of tools that you can just grab and immediately generate like fascinating results, like the project that we have just seen. But then it start to seems like people start to rationalize to see why are we talking about the style, why the style is happening in the digital age. But we have to be aware at this point, at some point, it's just this restriction from like the technology side. It's that we're not able to develop our own algorithm, so we're just being relying on what computer science are like really developing. So I think this is like one aspect that I like to work with, like material computation. It's just that because this one is pretty under investigated by computer scientists. Basically, no one can get the large amount of information on materials. And so a lot of the training and building up the model for this part, you have to build it up from like fundamental blocks, like the basic structures, instead of just throwing a pre-trained structure of like 50 layers. You have to start to taking on the like why you're choosing this layer, why you're choosing this activation function, and what works or what not. So it's like more conscious approach. I think there are a lot of people who are also on this track. So let me see if I can find like a reference. One moment. Oh, one moment. Let me just show this one. This one is like so I think this paper shows like ultimately what we're talking about styles. So this is like what they call the machine learning interdisciplinary AI. So basically they have developed a style transfer method. It's based on like a very similar process. It's downloading. So basically you can transfer, it's called interdiscipline. It's because you can basically transfer whatever image and onto whatever building. And suddenly you're having like this very sophisticated building system that of course, there are certain level of smartness in there, but a lot of them were like hard to describe. And a lot of them are like very visual based. It's because the algorithm is very visual based. The decision is based on whether this one looks alike or not. That's just the nature of how the algorithm works. So if I'll just put the paper here. So this is like a typical style transfer papers. So you can merge anything with anything with this method. And of course, this is on the more aesthetic side, but even the one that you're doing like with the layout, it's essentially the same system. It's not the layout they generate is much smarter than this. It's just that they're generating a layout that looks like a real layout. But there is like a lack of understanding on like why A is here and the 1B is there. What is the relationship between a bedroom or a living room? Those cannot be extracted from the system, but the system is just making the decision based on the like overall score of, let's say, likelihood. So like with this system, you can simply collage anything with anything. So this is more like 3D style transfer. And that's why like a lot of people start to talk about the style and style again. It's because it's one of the reasons is just because it's very prevalent in the computer science. Let me get another one that is like more rational. So this is like another paper. Let me see if we can find this one. I'll share this one in the chat. So a lot of things are going on in the world right now.
Dan?
Yes?
Yes, I agree with you. I like, I don't get it. Why maybe not everyone, but many people or groups that are working with AI now are talking about style when in the story of Rosen architecture, we should have like get rid of it, no? In a way that we're putting materials and we're trying to generate forms starting from the material performance instead of, let's say, copying different styles, because everyone is talking like, hey, let's create a Saha kind of building, no? It's funny because it's Saha the style that we want to look forward. And yeah, and I think one of the, let's say, great opportunities that AI can have us is just to have better performance building or better performance systems. So the question about if style guns is architecture or not, it could be very, let's say, debate, because it's funny when it can work if you can, if you want to do like digital environmental and doing architecture in digital environments like for gaming, AR, or VR. But when you go into the real world, then the real world is three-dimensional. So the work of Emmanuel Koch,
Yep.
I think that is very interesting because yeah, he's moving forward. He's making this change from 2D to 3D, including the material computation as the same as what we are doing. That's why I really found this workshop very interesting, you know? Because you are using AI in order to build, in order to operate in the material world, in the real world. So you're using AI to attack maybe some, let's say, gaps that conventional architecture approach can't achieve. So yeah, I'm very interested in, maybe if you have like any, let's say, if you know any project of people who's working with 3D AI, like with voxels or somehow, whatever.
So I think there are two parts of the question. Like one with people with 3D, because they do have 3D style transfer. So it doesn't really only happen in 2D space. Now they do have like people working in like 3D style transfer, like you said, making a Zaha Hadid building, make a building, train a neural network to generate a Zaha Hadid style building. And the second point, I think is very crucial, as you made, like working with like real matters and the real properties without being over reliant on what computer scientists has there to offer. So I have just shared a link. So this is one project that are did by another friend of mine, Zheng Hao in UPenn. And this one, I think it's sort of, let's say, it didn't really show the full potential of machine learning, because I do think the potential of machine learning is that its capability of doing what human cannot do and what traditional method cannot do. But this one does share approach, like let's say a perspective on machine learning. So basically this one, like I remember like earlier in this workshop, someone asked, sorry, I forgot who, if we can train things with like simulation. So this is a project that are trained with a simulation, and basically all their base data sets are created with finite element model. And they were but however, like the finite element model, as if I'm right, like it's just taking a long time to run. It's very computationally expensive, and so basically they just train let's say a neural net to replace that finite element model. So this is like one option that you can think of. It's like you start with a format of a very complicated structure system that are like, say, fairly impossible to be applied in large scale or at like a level of complexity, but you're able to, from like that material model or from that finite element model or material simulation, you're able to train a neural net that replace that simulation and or replace that calculation process, and then you can play like doubling up the neural net or transfer it to another function, etc., which generates something that are far more like efficient, like at least computationally efficient. Of course, my thing with this system is that it's already doing what another algorithm can do, but it's just essentially doing it in a method that are like quicker, but not necessarily better, but like a far quicker and easier. So this is like they do have a physical model behind it to understand how this one works. It's just that this one just taking forever to calculate, and they're able to build a neural network based on the simulation and expand it with a neural network. I do think there are essence in this kind of process that instead of based on like physical things, we're looking at, let's say, optimizing a simulation process or optimizing a calculation process. So I think those are like a direction you can look into. And the benefit of this direction is that they are like very quick output. You don't need to do any materials, and you just need to frame right questions, and you can just train it with simulations and etc. Let me see if I have some other examples. So another idea is that let's see. Trying to find something. Let me find another paper here. Oh. Let's see if we can find this paper. One moment. My computer is slow and killing me. Oh, excuse me. I'm going to share this one because I think this is another interesting examples of like work going on around with AI. Download. So the I'm not sure. It's okay. So this is like a project done by Sigrid in Aachen. So they're like the pioneer research on that robotic for fabrication. And for this, if I believe they're using AI, and I think it's this paper. Yep. So they're using AI to find solution space for the like path planning of the robot. Perhaps some of you are not very familiar with this kind of like robot construction. Like for a structure like this, optimization for the path planning of the robot is very difficult because for one thing, you need to make sure the structure is stable during the process. In the process of the assembly, and you have to make sure like the previous members cannot block the access route of the later members. So if you're having like very dense space and essentially there's no way for the robot arms to get in, it will be like very problematic for the fabrication process. So there are just a lot of interdependent aspects to optimizing this part. So I think earlier, a few years ago, we did a like path planning like study for a path planning research for a generic mesh model, and then like even a small scale mesh model, the optimization process take like 20, 30, 40 hours to find like the right path planning to make every step is right. So in this paper, I think they are using an AI method to train and make sure, let's say, at each individual step, the structure is stable, and at each individual step, we won't have this kind of problem like the robot knocking on itself, the robot is like locking itself in an awkward position, or the like robot is not like hitting people and etc. So basically this one is that they're using AI to find the solution space for the operation of the robot. I'm not exactly sure. I didn't really read every word of this paper, but so I'm not exactly sure what kind of neural net they're using. But I think this is definitely like one direction that we could work with to actually work with the fabrication process itself. So because like my personal interest is in the like fabrication and the material, so this is something that I'm more familiar with. But from the previous conference, I think there are a lot of properties also in categorization. For example, I don't know if people have encountered a problem. For example, you have a CAD files and all the lines are on like one layer. So do you want to, like I say, an AI that could just automatically change all the lines to different layers, like the doors to the door, like the windows to the window layer, and the wall to the wall layer, or the like finishing to the finishing layers? So I think there are like earlier in like IKD, I don't quite remember that papers, but there are a lot of people looking at this one. It's like this kind of automatic drawing process, so that you would have create AI models that could, when you input very messy CAD files, it can automatically label like which line belongs to the wall, which line belongs to the infill, which one belongs to the window, and etc. And automatically move like all the different elements into the different layers. So this is, I think, like another some ideas if you're interested in to expand your research, if you like with some at least some commercial values. And of course, there are like a mass amount of people working on AI for urban planning, especially like smart cities. One is like one benefit of this process is that now we're able to collect mass amount of the data for the cities to actually train a network that actually has its advantage in actually do things. So we're able to collect street views. We're able to collect like video cams, security cams from every corner of the city. And we can do a lot of things by just analyzing those video clips, like the earlier examples I have shown, like image segmentation to calculate how many people are on each corner, and we can relate this one to different data such as crime rate, such as housing, such as like traffic jams at different hours for the city planners to make a better decision on like traffic planning or traffic light. Because my husband work for a huge internet company called Baidu in China, and he's working on autopiloting cars, and they're like his firm is already working with government to use AI to optimize for the let's say the traffic lights and the urban planning of the region. So and a lot, I think a lot of their employees are like graduates in urban planning, or let's say people with design or architecture background. So I do think there are a lot of room for imagination for AI in the future, especially in architecture. But let's say you just need some imagination on what it can do. Yeah. Let's see this one. If we still remember this one. So I think this one is also at like 150 epoch. So this one is at 0.1. So I think the previous one is like 0.2. So I think like adding another layers definitely helped. So while we're having the conversation going, so anyone want to have another luck and say if we should increase another layer or add a few neurons to one of the layers? I'll just take a wild guess and add 2 layers, and each one is like very limited neurons, and see what happens. So normally, like as the neural net goes deeper, it does have the problem of being overly generalized. Like all the later neurons are become very even and inactivated. There are a few ways to fix this one, but I think like our 4 layers are not like deep enough. But if you're really using like a 50 layered neural network, they don't usually perform well for a variety of reasons, and they do need something like the let's say something similar to forget gates or this kind of thing to bring the information from earlier layers and combine with later layers to bring some details back in, because it's very easy to start losing details as your neural networks gets like really, really deep. Okay, so while we're allowing this one to train, so anyone want to raise any other topics? Feel free to cut in the conversation. I mean, we don't really have other content, so it's just because we're like the only team on AI in this, only workshop on AI in this conference. It's just very good as we're approaching end of the day to have some discussions and brainstorms.
Well, I think there are 2 questions in the chat box. Maybe you can check it.
Yeah, sorry. Term of data input, do you have a reference to the process? So I think it comes as 2 parts. Let's say the first one, the human behavior patterns. What do you mean by human behavior patterns? Does it mean like I go to sleep at 8 o'clock at night? Does it consider as like human behavior patterns? So just be aware, like for the inputs, you don't really need to make a logic of the inputs. I'll quickly sketch something here. So I'm going to use word processing as an example. Here's screen. So I just this one, get away this one. So there are 2 ways to find this one. So be aware that the neural nets are capable of finding things that connections people cannot see. So imagine like originally we're doing word processing, and basically we'll have a dictionary of word, for example, a apple, all the way to, let's say, zebra. So let's say those are like a dictionary of words. Let's say there are like 10,000 words in our dictionary. And ideally, they like each of them one will give a label. So this one, the label is, let's say it's 1, 2, and 10,000. Oops. And ideally, like not ideally, like in the most classical case of the like traditional case of word processing, for example, it's going to generate a sentence. I'm just using this one as a reference. For example, each word is your human behavior patterns. For example, this one is like walking slowly, or this one is like, or if it's a shopping, for example, this one is like buying a t-shirt that is like $20, a white $20 t-shirt, and this one maybe like buying, I don't know, groceries, buying apples or pears. So each one you can have like 10,000 different behaviors. Trust me, it's gonna cover all the human behavior categories of human behavior. So for this one, like originally when they started with like word processing, and when they will try to generate a sentence, so how do they decide on which word goes on here? So originally they will generate 10-dimension vectors for 10,000 dimension vectors for each of the locations. So for example, this one, like having a, like the possibility of having a is like 0.8. This possibility of having an apple here is 0.0001, and having a zebra is probably 0.0000, like very, very small. So basically, for this one, each word they will generate these 10,000 dimension vectors that outline like the probability of the each word being on here. So probably with this one, like the first word is like likely to be an A, generated to be an A, like apple a day, like makes doctor or whatever. So that's the possibility is very high for the A. But the problem, if you have observed in this method, because it's very comparable to human behavior. Basically, if you're just giving a code to each human behavior, it's impossible for them to recognize the connection between different human behavior. For example, in this one, it's the same in word processing. So that's why I'm saying, like, when we're working with machine learning, so you just need a little bit imaginations to connect different pieces together. So for example, we're looking at algorithms that are traditionally used for word processing. In this dictionary, there are a few things have similar process. For example, a and the. So probably those words have some similar properties. And let's say apple, or someplace here, pear, or someplace down there, like, I don't know, like the apple, pear, grapes. Like those words would probably have similar like properties. Not in terms of spelling, but as with the content of the word have similar properties. The same as goes for human behavior. So even though like some human behavior may have a connection with each other. So for example, like a zebra, and some place here may have a word called dog, and some place here may have a word called cat. So maybe they have like certain similarities between each other. In this case, before they start to like in a more newer, like, so it's not that new, but like a later part of word processing, they will have an alternate method of coding those things. So instead of having this kind of 10,000 dimension spatial vector to describe them, just basically assign to one of them a number. They will start with actually, so this one is also through machine learning. So they will have firstly like a machine learning process to see. So those are like a apple. You need to check on what this process is. I don't really remember how this one achieved, but like the basic concept is that each code, apple, pear. So yeah, they start to train. just drastically reduced from 10,000 dimension to an encoder that each number apple or pair, or let's say king and the queen, are giving like a 40 number to describe its property, not its location, its property. For example, apple may have like 1, 0.5, like 0.003, and its king may have something like 0.8, queen have like 0.9. And if I'm just putting in a term that human can understand, those are the properties that describe those words. For example, it's likely like this property means royalness. If this word is very royal, so obviously king and queen are very royal, and the apple is, maybe it's a bit royal, so let's make 0.01 because it appears in the Snow White. And obviously apple, so maybe this one is like means fruit, or it's edible, means it can be eat. It's not poison. So obviously apple are edible. You can eat apple, but maybe you cannot eat a king and you cannot eat a queen unless there are like some weird scenarios. So basically there is a way to train this kind. So this is not something human created. So this is something like art. So this is actually a side product, like a byproduct. It's a byproduct of the neural network training to generate this like a matrix of information to describe each individual of the words. I'm not, and I would assume, because I'm not really sure like what exactly you're looking after, but I would say if you're looking at the human vectors or human behaviors, try to use this method to create this kind of dictionary for human behaviors, train this kind of like spatial vectors to describe like the essence of each human behaviors. And there are a lot of things you can do with this one. Of course, when you're using this system to train the like encoders to train a speech recognition or speech generation, the accuracy will be much higher and much more efficient. It's because essentially you can capture the relationship between the words. And also another possibility is that with this kind of spatial vectors and comparing the each individual numbers, you can get like the spatial distance between the word. So in this case, so apple here and the pair here. So if this is like a vector space, so apple and pair is probably very close. King and queen is probably also very close, but while like those are very far away. So if you use this method to structure like what do you say, unstructured data such as human behavior, you're able to like with this byproduct, you're able to let's say categorize and find the connections between human behaviors. Maybe there are certain behaviors that are more close related to one or not, but I'm not sure what you're going to find out. But this is like a very interesting data analysis method to build up connections. Yeah, maybe. So one moment. I don't know, Riva, is this the answer you're looking for, or am I on the wrong track, barking up the wrong tree?
It is pretty much depict what I'm searching, because I'm trying to understand how can I validate the properties of something that I'm seeking. Like this example is the edible or the royal properties that structured apple, king, and queen.
Yeah, I think this is like a very interesting like idea, and brings a lot of attention. Of course, there are like heavy math involved. And but just remember, I think if you're looking this direction, like those are just some properties that I'm using as a reference because human can understand, but in fact those properties are automatically trained in the neural network, and they're likely to be some very abstract properties that like no one can understand. So for example, why this happens is that, let's say we're going to describe like grandpa and like granddaughter, so we can have like 2 dimension to say age and gender. So if we're having a vector like properties values going along these 2 axes, human can understand. However, like during the training process, it's likely like the output of the vector, like the vector they use, even though they're still perpendicular, it's likely there's something like this. So this one is likely to be your property 1. And this is property 2. So those are not going to be like neither gender nor age. It's just going to be some very abstract properties that only computer can understand. But nevertheless, this is you can still use this kind of like abstract properties to evaluate like how close maybe these two people or these 2 elements are. So it doesn't influence like the evaluation of how close they are, what's their like if one influences the other or not. It doesn't influence the logic. It's just that they're not, let's say, interpretable by the human. And if you want something working in a more interpretable manner, you should look into the more classical machine learning method, not the neural network. Let's move on to the next one. So you mentioned that generation process of GAN is unexplainable. What's way to mix other training models classical? So I think it's a good question. So the GN is very unexplainable, and yes, you can mix this one with traditional machine learning models, but just be aware, like the traditional machine learning model is not as strong as the neural net. So that if you're trying to generate, so the benefit of the neural net is like we're able to have like the one we have shown before. It's like you can capture higher dimension properties that are not picking up by human. But if you're trying to limit it to a system that are like can be understood by the human, by default you will be eliminating a lot of this kind of very higher dimension abstract factors, abstract features that also contribute to the process. That is part of the reason why neural net works a lot better than the traditional machine learning method, is that it can pick up these very high dimension properties that human can interpret. So I think it's also, I think one of the examples that in the previous discussion comes up for you regarding the GAN network. For example, let's also begin with like this kind of street view generation. And you can have a generative. So this is like generative neural net, like our painter that also do like maybe you can just paint it to like, I don't know, Amsterdam. Yeah, something like that. That they can actually like paint a street view. And of course, instead of having this one, so basically for neural network to work, it just needs a score to tell it how good it is on different dimensions. So basically, it just needs a score. It doesn't really care if the score come from another neural net or it come from another machine learning method. So for example, this one we can use traditional statistic method to evaluate. I think I'll give it like a dimension of like percentage of green and percentage of pedestrians, percentage of cars, how many cars are here, and so on. And we can also use like statistic method to compare this one to, I think what the previous example is Manhattan, and this one maybe we have someone from Melbourne. So let's say use Melbourne for example. So to compare this one to the score of Melbourne to tell how similar is this thing with Melbourne. And eventually, like so this one to generate a score of similarity with Melbourne, and they use this scores to calibrate this generative model. But of course, the result, intuitively speaking, in the end, this generative algorithm is able to generate like street view or something that doesn't really looks like street view. So maybe like the windows can be all over the place, and the trees maybe in the middle of the road or on the top of the road or somewhere. But essentially it will generate a drawing that has the same percentage, but it doesn't have like the same underlying connections. For example, trees have to be alongside the road, or like windows have to align. So it doesn't have these kind of properties. So basically this one will like not as performative as like typical let's say as a typical GNN neural network. But of course, under certain scenarios, if you're not talking about image generation, but if we're talking about, let's say, real estate housing price and just the numbers, maybe this way can work. Like you can have this part in a more understandable assessment. So in this way, the assessment is how much like the similarity score to Melbourne based on the percentage of each element. And maybe for the real estate scores, it may be like based on the score to the ideal real estate distribution or ideal real estate development to generate a score. So that if we only work with statistics, I think it at some level it still work. But it's if we're talking about these very high level abstract features, such as like image generations, this kind of like traditional machine learning will have a lot of difficulties because it just doesn't capture those kind of nuance of features like where the window is, where the door is, and etc. So just so the short answer is that yes, it may work, but if that's gonna work, you have to be very careful and conscious about what is the input value and what is the expected output, because this one will not be as powerful as neural net to capture all the details. So Hoi, so does that one covers your question? So no worries. So if anyone has any more questions, feel free to post in the chat or just speak up. All right, let's just take another look at this one. It's still going down. Just give me a second. So very good. So I think we're approaching the end of the workshop, and thank you everyone for spending the very intensive last 3 days here. And if you guys still have more PDF, please send to Zhu Guanqi because he really needs to do this video. Yeah, good luck. Feel free to share your thoughts and questions on the in our chat room or in the WeChat or WhatsApp app. Yeah. Thank you everyone, and let's keep connected.
Thank you so much.
Thank you.
Thank you.
Yeah, really. Thank you very, very much. It was really interesting.
Yep. Have a good day. Bye-bye. Yep.
And thank you, Guanxi. Thank you.
Bye-bye.
Bye. Bye.
再见。